This is lesson 2, introduction to Fourier transform of discrete time signals of signals and systems. In this lesson 2, we'll have these 4 subsections. We'll first interpret Fourier transform. We'll discuss the 3 types of Fourier transform that we're interested in, which is DTFS, DTFT, as well as DFT. We'll provide some examples and the properties. Let's interpret Fourier transform. If we are given a signal x of t, basically Fourier transform tells us that it can be decomposed into sum of sinusoids. In this example, we say that we can use cosine of all the frequencies that we are interested in, and as long as we can multiply correctly the magnitude at that particular frequency with the phase shift, we can reconstruct xt. And if xt is periodic, we call it Fourier series, and if xt is aperiodic, we call it Fourier transform. Now, if you open up books on Fourier transform, you can read about Fourier transform trigonometry series, as well as complex exponential series. Actually, both of them are representing the same. They are in fact just representing some cosine at some frequency multiplied by the respective amplitude with the phase shift. In trigonometric series, they are using cosines and sines of the particular frequencies to generate the corresponding phase shift and the magnitude. The complex exponential is a little bit more advanced. It actually uses exponential ej theta or ej omega t to represent cosines and sines. We'll see a detailed description later on. But the take-home message now is this. Xt, if it's periodic, can be represented as scaled versions of cosines with the respective phase shift. Now, let's have one example here. Let's have this example, this red guy here. And by Fourier series, because it's periodic, by Fourier series, we realize that it could be broken down into a cosine multiplied by 2 at this frequency, 2 pi 5 omega, with this phase shift. And at 2 pi 10, we should multiply by 1, the amplitude, but with this phase shift. So xt, we didn't know what it was, but Fourier series tells us that it was made up by these two. And this is an equality. It means that actually this xt could have actually been generated by this sum of these two cosines at these two frequencies with this scaling factor as well as this phase shift. So once we have this, then this is really Fourier series. Fourier series convert x of t into this sum of cosines at their respective frequencies. Now, we can view Fourier series like this as well. The red guy is what we see, but it's actually made up of this dashed line blue and this smaller dashed line blue of higher frequency. This in fact is a nicer diagram. You show that omega is here, and this is the sinusoid frequency y of the amplitude, and this is time, and you see that actually it's one cosine adding with another cosine of different frequency. So now I can tell you that this guy is 2 pi 5. This is 2 pi 5 omega. This the first guy. And the second guy, this omega, is 2 pi 10. Alright, now, we don't like to draw a diagram like this because it's so complicated. Let's have a simpler way to draw this representation. So what's the clever way? Well, we make this axis omega, right? Because see, this is frequency. So this line here is frequency. And at this frequency, omega 1, at 2 pi 5, we're going to draw the amplitude 2, right? Which is this 2 over here. And at at omega 2 at 2 pi 10, which is this frequency here, the amplitude is 1. So we draw the 1 here. So you see, in this nice diagram of representing x of t as a magnitude spectrum, we immediately can see that, oh, actually our red line is constructed by two frequencies. One at 2 pi 5 with amplitude 2, and the other one 2 pi 10 with amplitude 1. But of course, this is not all. We need also the phase, right? Because when we have amplitude alone, it's not enough because we need the phase shift. So in the phase shift, for the 2 pi 5, we have minus pi over 4. At 2 pi 10, it is plus pi over 6. So look at this diagram. At 2 pi 5, we have minus pi over 4. At 2 pi 10, we have plus pi over 6. And there is no other signals here. Okay, so this diagram here is called the phase spectrum. The top guy, magnitude spectrum. In fact, when we talk about Fourier analysis, we are actually going from x of t into this diagram. Where are the frequencies that can or should be used to construct x of t? And at this particular frequency, we know there is amplitude and we know its phase. So this is the take-home message of the idea of Fourier transform. How we do it, we'll explain it later. Thank you.